So today we're looking at section 2.4. So the point is we've done the algebraic properties of the real numbers, the order properties of the real numbers, and last Friday we did the supremum property. Okay? So now we can actually say anything that's true about the real numbers you can prove from the axioms that we've established. Okay? That's kind of a meta-mathematical result. We're not going to prove that. But it is true that everything you can prove about the real numbers, you could do from the axioms. And that's kind of the point of the axioms. For the rest of the course, we're going to be proving things about the real numbers. And we can rest all of that on these axioms that we agree on. Okay. So today we're really going to look at how we use that supremum property. So let's start with something that's hopefully a little bit obvious, but, well, let me just state it. And let me see if I can spell this right. The Archimedean property. I'll state it and then we'll talk about it. Okay. For every real number x, there's some natural number n that's bigger than x. Okay. And I hope everyone agrees that this is an obvious statement. This is obviously true of, it's stated as a statement about the real numbers, but it really is a statement about the natural numbers. There is no largest natural number that keep going on forever. Okay. Now, the slightly surprising thing, and again, this is the kind of meta-mathematical thing we're not going to prove, but the surprising thing is you can't actually prove this without the supremum property. Okay? You just use the algebraic properties and the order properties, you won't be able to prove this thing, which is a little bit surprising, I think. And then you might ask, well, it must be true for the rationals too. Well, there's a different property we can use to prove it for the rationals, but that's beyond today. Let's prove this. Suppose the statement is false. Okay, what does that mean? So there is some x in R such that, well, what would it mean that there's no natural number that's larger than it? It would have to mean that they're all less than or equal to it. Okay, that's essentially a trichotomy. So n is less than or equal to x for all natural numbers n. Okay. Now, the supremum property says, well, supremum property applies to non-empty bounded sets. So this means, let me write it that way. This implies that N is a non-empty set that is bounded above. And what I probably want to say non-empty subset of R, just to emphasize that that's where we're doing things. Okay, and so what does this mean? So the natural numbers has a supremum. It's by the supremum property. So let's let U be the supremum of the natural numbers. Okay. We assumed at the beginning that the statement is false. So we want to derive a contradiction. Anyone have any suggestions for the contradiction we're going to derive?
We could show that U isn't a supremum.
Mm-hmm. Yes, we do want to show that U is not a supremum. And how would we do that? All right.
Consider U plus 1.
Mm-hmm. This is good intuition, but what does U plus 1 get us?
Well, a number larger than U, but U is supposed to be larger than all the natural numbers.
Mm-hmm. Okay, so if we're trying to show that U is not the supremum, then we're going to contradict the upper bound property. Okay. Now there's two things to being a supremum. One is you're the upper bound. The other is that you're the least of the upper bounds. So we're going to contradict the upper bound property. So we need a natural number that's bigger than U. And U plus 1 doesn't need to be a natural number. U doesn't need to be a natural number. Okay? From what we've proved, right? So how are we going to find a natural number that's bigger than U? So here we have a cute trick. We're going to use the least upper bound property of U. Okay? So if we subtracted 1 from U, that would be a smaller number than U, right? So that cannot be the supremum of the natural numbers. Which means that there must be a natural number that's bigger than U minus 1. Okay? So that's what we're going to do. Since U minus 1 is not the supremum, of n, there must be some natural number, I'll call it m, which is bigger than U minus 1. Okay. Now we can add 1 to both sides. Okay, because we know if we add 1 to a natural number, we're still a natural number. Therefore, m plus 1 is greater than U, and since n plus 1 is a natural number, this is a contradiction to our assumption that u is the supremum of the natural numbers. And this contradiction finishes the proof. Okay. Are there any questions on that? It's not for such an obvious statement, the proof is not so obvious, I would say. Okay. It's not the first proof you'd think of. In fact, if you're staring at that statement, you don't necessarily think of a proof at all. And that's just because this is a good proof to do this on. Let's just kind of think through the major steps here. We assume that the statement is false. Because the statement was false, we were allowed to say that the natural numbers have a supremum, and we called it u. And then what did we do? Well, we contradicted that implication. Okay, so the statement being false implied that there was a supremum, but then we contradicted that. And because we contradicted the implication, we've contradicted what we initially said, what we initially assumed, that the statement was false. Okay. Okay. Did any questions pop up while I was going through that?
I have a quick question.
Sure.
Could we have used x in this proof instead of u? Because isn't technically x also an upper bound?
Yeah. Yeah, certainly. Yeah, we could have. You'd have problems. You'd have problems at the end getting that.
It's an upper bound, but it's not necessarily a supremum, right?
Yeah. So if you tried to derive that final contradiction by using x, what would you do? You'd want right here to say that m plus 1 is greater than x. Okay, but you're not going to be able to do that because you can't do this part. You can't say since x minus 1 is not the supremum of...
Oh, okay.
You can't get this part.
Mm-hmm.
You actually need the supremum.
Thank you.
So the only thing x is doing for you in this proof, right, the only thing that x is doing is giving you the initial bound so that you can use the supremum property. Okay, we got this bound on all the natural numbers, and then we got to use the supremum property. That's all x did for us. And we argued our contradiction with the supremum itself. Okay. Okay. Couple consequences of that we're going to go through. I should warn you. The last time I taught this course, for some reason, everybody used the Archimedean property all the time on their proofs. It's a very important property, but we don't use it very much. I'll just warn you. If you're using it in every proof, something's gone wrong. Okay? And in fact, when we do use it, we don't really need to say that we're using it. I mean, the Archimedean principle just says there is no largest natural number. Okay. When you need to use that fact in one of your proofs, I don't insist that you say that the Archimedean principle told you it was true. Okay. Just you're allowed to say there is no largest natural number. Okay, but the formal name is the Archimedean principle. Okay. We're going to do two corollaries. Let's do them slightly out of order from the book. Okay. Corollary 2.4.5 is frequently very handy. Okay. The statement is just for every epsilon greater than 0, there is some natural number n with 1 over n less than epsilon. Okay.
Does epsilon have to be at most 1?
No. Oh. No. If epsilon's bigger, then we're fine. Right? The set of
Less that. Okay. Yeah, I was reading equal for some reason. Okay, that makes sense.
Yep. So the point is that these numbers are going to go to 0. Except, let me just point out that in this course we have not talked about that concept yet. Okay, we haven't talked about what it means to go to 0. We haven't defined limits, anything like that. Okay? But informally. Okay, now I'm just realizing that I'm doing these slightly out of order. So what... Well, let's just see what happens, okay? This is not the proof I'd prepared, but... Okay. Suppose otherwise. Okay. Now so there is some epsilon. There's some epsilon greater than 0 such that there is no natural number whose reciprocal is smaller than it. Okay? What that means is that there's some epsilon greater than 0 that is a lower bound on the set of reciprocals of natural numbers. I mean, I don't even know why we're doing this much. Let me. Yeah, I'm sorry. I'm going to erase this. I don't know why our book does it this way. I think it's easier than this. Okay, sorry, new proof. By the Archimedean principle. There is, and okay, there is some natural number with n greater than, well, I want n to be greater than 1 over epsilon. And now I just want to use the order properties, right? I can, epsilon is greater than 0, so I can multiply both sides by epsilon. Since epsilon and n are both greater than 0, I should say, this implies that epsilon is greater than 1 over n. Right? I'm just taking that inequality that we had here, and I'm just multiplying both sides by epsilon, and then I'm going to multiply both sides by 1 over n. And I'm going to get epsilon is greater than 1 over n. And that's what we wanted to prove.
So basically, you're using the Archimedean property or principle to say that, like, there's a larger number. How did we just use the Archimedean principle for that? We're saying because there's a larger number?
Yeah. Hold on. First, let me fix that, because you're right. We didn't call it the Archimedean principle. We called it the Archimedean property. And then what did it say? It said for every real number, there's a natural number that's bigger. Okay? Go back to where we used it. 1 over epsilon is our real number. And the Archimedean property says that there is some natural number that's bigger.
That's what I thought. Okay, thank you.
And then I'm making this thing about them being greater than 0, because otherwise I can't solve that inequality the way I want to. Yeah, so I don't know why the book does it the way they do it. And I hadn't realized that when I was reading the book earlier today. I'm going to make this proof a little bit better, if it's okay with you. I think this proof would be a little bit better if we said, let epsilon greater than 0 be arbitrary at the beginning of the proof. Okay, just be clear what our variables are. You can basically get away with it in this proof, but you really should define all your variables in the proof. Okay. Okay, any more questions about that? A couple more corollaries. I'm not going to spend too much time on them. The proofs are in the book. Corollary 2.4.4. You'll notice this is a lower number. The book does this first and then uses this to prove the one we just did. I'll write it this way. We have the infimum of this set of 1 over n that infimum is equal to 0. I'll leave the proof to you, but let's just think about it. It's an infimum statement. So there's really two things to prove. One is that 0 is a lower bound. And 2 is that there is no smaller. Sorry. It's least upper bound and greatest lower bound. There is no greater lower bound. Okay, two things. The first thing, why is 0 a lower bound? That follows from the order properties. Okay, the way I would do that part is we know that for any n in the natural numbers, n is greater than 0. So 1 over n is greater than 0. Does that follow? I mean, if this came up in a proof, that would be fine with me, that 1 over n for any natural number is greater than 0. Okay? I think the way you might actually have to do it is you'd have to say n is greater than or equal to 1, if you want to use the axioms we've written. So 1 over n is... No, I'm gonna go back to what I had. Okay. This just follows easily that 0 is a lower bound. We'll just assume it follows easily. Why is there no greater lower bound? If there were some greater lower bound, what would that be? That would be an epsilon greater than 0. Such that epsilon is a lower bound. Such that epsilon is less than or equal to 1 over n. Okay? But that's a direct contradiction to the corollary we just proved. Because the corollary we just proved said if you've got any epsilon greater than 0, there's some natural number n with 1 over n less than epsilon. Okay, so none of those numbers could be a greater lower bound. Okay. Any questions there? And like I said, the book does these in the other order. So go ahead and look in the book and see if you can make that make sense. So they do 4 first and then derive 5 from it. Okay. The last corollary of the Archimedean principle is 2.4.6. If you've got a real number y that's greater than 0, then there is a natural number n with n minus 1, well, y is between n minus 1 and n. Okay. The proof of this, again, I'm gonna just say a few words. I don't think we have time to write it all down. But what you want to do to get this n on the upper bound side, you want to look at the set of natural numbers that are, let's say, greater than or equal to y. Okay? Now, this set is non-empty because y
because
we
of
just
the
prove that they're.
median property.
Yeah.
Mhm.
It's not empty because of the Archimedean property. And then it's well ordering. It's well ordered, so we have this well ordering property. It has a least element. Okay, call that least element n, and then n minus 1 cannot be part of that set because n is the least element of that set. So what does that mean? That means that n minus 1 is actually less than y. Okay. So that's the sketch of the proof. And again, to write out a proof, the important things to remember about proofs in this course is that they are comprised of complete sentences without logical symbols. And so you write out a proof for this, you want to put it in complete sentences, like what we've been doing in class. Okay.
I have 2 questions about that last statement.
Of course.
So, can we is it a strictly less than, since we're using the well ordering?
Yeah.
Because if they're equal, then you'd pick the top one.
Yeah, do you mean this part? The n minus
Yeah.
1? Yeah. Yeah, that would be strictly less than because it's not part of this set.
Okay. And then about proofs in general, about using complete sentences and not using logical symbols. Does that mean where we're writing here, n is a natural number with n and n, is that still okay?
Yes. The only logical, and I'll send this out in my email, but the only logical symbols you're not allowed to use are like for all, there exists, implies, if and only if. Okay? So the symbols that take the place of I hope it's clear what the group that's forbidden and the group that's not forbidden. So in
we
and
could
subset
use
and all those are allowed.
A subset and stuff like that are allowed. Okay.
Yeah.
Okay, got it.
And I tried to mark on your homeworks. I tried to point this out, and I didn't take off any points this time, but in the future. Okay. Other questions? So there's a lot in this section. This is the Archimedean principle property and its corollaries. Next. This is what we would call the algebraic properties of soup. And inf. Okay, there's a bunch. It would take too long to do proofs of all of them. I think we get time to do a proof of one of them. Basically, soup and inf work like you think they should. So let's say that, suppose S is some subset of the real numbers, and it's non-empty and bounded above. Okay, that's what we need in order for it to have a soup. Now take some other real number. Let's call it little a, and let's define let's define A plus the set S to be the set of A plus little s for all elements little s of the set S. Okay. This is not just for this example. This is throughout this course. This is what this is going to mean. In fact, throughout mathematics, this is what it's going to mean. But it might not have come up for you before. Then we have the sup of A plus S is equal to, I hope you can guess, it's just going to be A plus the sup of S. Okay. There's two things to prove here. Okay. You want to prove that this is the sup, so you want to prove first that this is an upper bound on A plus S. Okay. And two, that there is no smaller one. There's a smaller bound, upper bound on A plus S. Okay. Let me see if we can take a crack at that real quick. Okay. To show that it's an upper bound, you need to take an arbitrary thing from A plus S and show that it's less than or equal to A plus the sup of S. Okay. So, proof. Let little s and s be arbitrary. We have s is less than or equal to the sup of s, because that's what sup means. Okay. Now in your proof, you could say right here, you could say by definition, but when it's so obviously by the definition, we don't really need to say it. Okay, so, and now this is by the order properties, but again, we don't really need to write that. A plus little s is less than or equal to A plus the sup of capital S. Okay, well, I'll put a period there, and then the point is, since s is arbitrary, this shows that little a plus sup of s is an upper bound on A plus S. Okay. Now, to get the least upper bound part, it's a little bit trickier, so let's look at that. Let V, I guess, be any upper bound on A plus sup S. Okay, so V is an upper bound on A plus sup S. So if I subtract off A, I'll get an upper bound on sup S.
Is it a bound on A plus sup X or A plus S?
It's an upper bound on the set A plus, oh, sorry, not the set, the number A plus sup S.
Okay. So we're taking...
Oh,
so
I'm sorry, what am I saying? No, you were trying to help me here, and I got it wrong. It's an upper bound on the set.
Okay.
A plus S. And that's the point. So v minus a is an upper bound on S. Okay. Now, we know the sup is the least upper bound. So this means that v minus a is greater than or equal to the sup of S. So v is greater than or equal to a plus the sup of S. So indeed, what have we shown? We took any upper bound, v was any upper bound on a plus s, and we showed that it's at least a plus the sup of s. Okay. So we have shown, this implies that a plus the sup of s is the least upper bound of a plus s. Okay, and if we want, at the end of that, we can add a as desired. Okay. Any questions? Let me just point out, I say that your proofs have to consist of complete sentences, but I don't say they have to be linguistically beautiful or anything. Here we had a bunch of inequalities. I wanted to string them, or a bunch of facts. I wanted to string them all together. So we can just be lazy like that. I mean, it's a sentence. Okay. The important thing is that it's a sentence. It's not that it's a good sentence.
How do you go from v being an upper bound on the set a plus s to v subtract a just being an upper bound on set s by itself?
Oh. So if you want to expand that out, and I don't think it's necessary for the proof, but what do you know? You know that, and I am going to use the logical symbols here, because this is what they're for. They're for shorthand. Okay. So we know that it's an upper bound. So v is greater than or equal to a plus little s for all s in S. And so v minus a is greater than or equal to s for all s in S. Okay, and that's what I claimed, is that v minus a is an upper bound on the set S. Okay. We just have a couple minutes left, so I'm just going to conclude by telling you a couple theorems that are in the rest of this section. It's kind of a long section. Theorem 2.4.7. There is a real number x. In fact, it's positive. With x squared equal 2. Okay. We've noted before this that the square root of 2 is not a rational number. And this theorem is confirming that there actually is a real number, which is the positive square root of 2. Okay. The key to the proof, we don't have time to do the proof, but the key to the proof is you look at the set of all the real numbers, little s, such that we only want the positive ones, or the non-negative ones. Actually, we might as well say positive. that their square is less than 2. Okay? And then you'll want to take, this is a non-empty set. It's non-empty because like 1 is in there. It's bounded above because I don't know, any number that's 2 or greater is not in there. And then you'll want to, so it has a supremum, so you'll let x be the supremum. And then you'll argue that x squared is actually 2. Okay. And the argument is basically if x squared were less than 2, right, it has to be less than or equal to 2. It couldn't be greater than well, I'm sorry. This is 2 parts. You'll say that x squared cannot be less than 2, and you'll say that x squared cannot be greater than 2. Okay, and it's in the book, and I'm basically out of time. I am out of time, so that's what I'll give you for that proof. And then, if you think back to the Archimedean property and our corollaries of that, one of the corollaries that we didn't write down that we should have, again, proof is in the book, is the density theorem. So if x and y are real numbers with x less than y, then there is some rational number between them. Okay. And that just falls out of the Archimedean property. Or more specifically, that corollary where we showed that for any real number, there's a number 1 over n. Any real number that's greater than 0, there's a 1 over n that's smaller than x. Okay. So I'm sorry for running over. I will